Hello students, this is the chapter of chemistry of p block elements that we are going to discuss today. So today the topic actually consists of group 15 and 16 elements of that is are actually going under the p block elements. This is the second section of p block element. In the last chapter we have discussed about the group 13 and the 14 elements. So in this session we will be discussing about the group 15 and 16 elements. So this is the general trend of the group 15 elements. So you know the group 15 element starts from the element nitrogen, then there is phosphorus, then arsenic, then we have antimony, and lastly we have bismuth. So if we go from top to bottom, the group resembles like this: nitrogen, phosphorus, arsenic, antimony, and bismuth. So as we go down the group, as the principal quantum number increases for the elements, the size of the atoms also increase. Now these group 15 elements have a general electronic configuration, that is NH2 NP3. So if we draw the orbital here, then we are having these 2 electrons in the ns orbitals that are actually paired, and 3 unpaired electrons in the p orbital. So this is the general electronic configuration for any group 15 element. Now you see the p block configuration is here p3. You know that is p orbital can actually accommodate electrons mostly in the range of 6. So from 1 to 6. And you know that is the principal quantum number, and actually the amount of the number of electrons that are actually possible to fit in the p orbital is 6. And the half filled and the full filled actually orbitals are very stable. So configuration 3 and configuration 6 are stable, because the half filled or the full filled orbitals electronic configurations are very, very stable. Now you see, since the electronic configuration of group 15 elements is P3, that is the half filled electronic configuration. That's why this configuration is very, very stable. Now, in the next section, if we consider about the general trends of group 15 elements, first one is the atomic or ionic radii. Now it increases down the group, because I have already mentioned, if we go from top to bottom here, since the principal quantum number, that is the n, increases, that's why the atomic or the ionic radii increase. In the section C, it is the ionization enthalpy, that is decreasing down the group. You see, as the principal quantum number increases, the size of the atom also increases. And if you see, there is the ionization enthalpy. So if we have an atom and here we are having an electron, so the amount of energy that is required to pull off the valence electron in the gaseous state is the ionization enthalpy. Now you see, ionization enthalpy is actually higher than the group 14 elements. Here I have mentioned that is the ionization enthalpy is higher for group 15 elements than the group 14 elements, because the group 14 elements are having the configuration P2, but group 15 elements have the electronic configuration P3. And since you know that is the half filled orbitals configurations are more stable, so P3 is more stable electronically configuration than P2. That's why the amount of energy that is required to pull off the valence electron from the valence shell, it actually is higher for the group 15 elements, much greater than the group 14 elements. That's why group 15 elements have higher ionization enthalpy than group 14 ones. This is actually decreasing down the group, because you know, as the size of the atom increases, the amount, the nucleus, the power of the nucleus on the outermost shell or the valence shell also decreases, because the distance from the nucleus and the valence orbital actually increases. So the more actually becomes the distance between the nucleus and the electron, the less will be the attraction. So less amount will be required pull of the valence electron. That's why if we go from top to bottom, the ionization enthalpy decreases. But in general, the amount of energy required to pull off the valence electron for group 15 elements is much higher than the group 14 ones. And this is the reason. Why? Because the half-filled electronic configuration is actually very stable for the group 15 elements. Now, we shall go to the next section, that is the electronegativity part. So as we have come to the p block element of group 15, now we have to consider one factor, that is the electronegativity factor. Now this electronegativity is also decreasing down the group. This electronegativity, because in a specific period or in a specific group, if we go from top to bottom, the electronegativity of the atom generally decreases. So if we go from nitrogen and in the topmost we have bismuth. So bismuth is actually a metal which is electropositive in nature. But nitrogen is actually a non-metal. So nitrogen has an electronegativity in the Pauling scale as 3.0, where bismuth is an electropositive metal and it has electronegativity in the range 0.6. So that's why nitrogen is actually having much more electronegativity than bismuth. In the next section, if we can talk about the oxidation state of the group 15 elements. So firstly, we will start with the elements nitrogen. So general oxidation states of these group elements are -3, +3, and +5. Because you know the general electronic configuration is NS2, NP3. So there are 2 electrons in the s orbital and 3 electrons in the p orbitals for the group 15 elements. And if we actually divide these 3 electrons, the oxidation state will be +3. If we can snatch away all the electrons from s and p orbitals, it will be +5. So -3, +3, +5, these are the general oxidation state of a group 15 element. But except this, there are several other oxidation states too that are actually less common or more or less important oxidation states, but they are actually important in terms of some compound formation. So here the nitrogen shows some oxidation state +1, +2, +4. Phosphorus also shows +1 or +4 oxidation state. But the general oxidation state is -3, +3, and +5. So in this chapter also, we have to actually talk about some anomalous properties of nitrogen. So in the last slides also, I have told you that the first element of a specific group is actually able to show some anomalous property. Some anomalous property that is actually quite different from the other elements in the same group. So here also, since nitrogen is the first atom in this group, it shows some anomalous property rather than the other group members, that is the phosphorus, arsenic, antimony, or bismuth, you say. So nitrogen has some strange properties. So these are the reasons why nitrogen is able to show some anomalous property. First one is the very small size of nitrogen. Since the principal quantum number of nitrogen is 2, so its size is actually very small compared to the other elements in the group. It has such a high electronegativity. Recently I have told that in the Pauling scale, the electronegativity of nitrogen is 3. So it is a highly electronegative element. It has some high ionization enthalpy because it has the electronic configuration 2s2, 2p3, and to pull off the valence electron of 2p, that is actually quite close to the nucleus, is the energy required is very high. That's why the ionization enthalpy of nitrogen is quite high. High electronegativity, high ionization energy, And lastly, it is the one of the most important factors that actually govern the anomalous properties of nitrogen is the non-availability of d orbitals. The principal quantum number of nitrogen is 2. And for 2, there is no d orbital. Because you know the d orbital starts from n equal to quantum number n equal to 3. So from n equal to 3, the d orbital actually starts. But since nitrogen has principal quantum number 2, that's why it does not possess any d orbital. That's why it cannot expand its octet more than, or it cannot actually expand its valency also. So for these reasons, these are the properties that nitrogen show. And this is the anomalous properties you can say that nitrogen shows. The first one is the unique ability to form p-pi multiple bonds. You know nitrogen atom is a very small in size and it has 2s and 2p orbitals. And since these 2p orbitals are very small in size, that's why the 2p overlap, the p-pi multiple bond formation is actually feasible for nitrogen. That's why the molecular dinitrogen remains as a species N triple bond N. So this is the molecular structure of molecular dinitrogen, that is N2. That's why it can form this p-pi multiple bonds. You see the other element, that is the next element is phosphorus, which remains as P4. So P4 has some geometry. P4. So P4 has this geometry in this tetrahedral fashion. This is the geometry of P4. Here you can see there are single bonds, that is actually s orbital overlap between two phosphorus atoms. No multiple bonds or no p orbital is involved in case of phosphorus. The reason is since phosphorus is having 3p orbital and 3p's are larger in size, that's why p-pi multiple bond is not actually possible in case of phosphorus. But since nitrogen is smaller in size, the 2p orbitals are also smaller in size. That's why it can form efficient p-pi multiple bonds. That's why molecular dinitrogen is presented as N2, where there are triple bonds between nitrogen. But here in case of phosphorus, the single bond s orbitals or the sigma orbitals are actually available. That's why no double bond is present in case of phosphorus atoms. That's why that is the unique ability of nitrogen to form p-pi multiple bonds. You see the dinitrogen's bond enthalpy is also very high, in the range 940 kilojoule per mole. You see, because of this triple bond present, and to break a triple bond, a very high energy is required. There is one sigma bond and 2 pi bonds in case of molecular dinitrogen. And to break these 3 bonds, 1 sigma and 2 pi bonds, is the energy required is very high. That's why the molecular dinitrogen has a very high bond enthalpy, 941.4 kilojoule per mole. That's why when you see, when our atmosphere actually contains 78% of molecular dinitrogen. Because nitrogen is very stable molecule, and that's why in atmosphere, in our air, 78% is actually consisting of by molecular dinitrogen. So from now on, if someone asks you why there are so much of dinitrogen in case of in air, so this is the reason, because of such high bond enthalpy, 940 kilojoule per mole, which is quite difficult to break. Second is the covalency, that is actually restricted to 4. You see, there is the bond parameter. If you actually draw about the bond parameters here, you see here in case of dinitrogen. So we are having this s orbital and we are having these 3 p orbitals. So here we have 2 electrons and here we have 3 electrons. So from these 3, the 3 covalent bonds can be formed by nitrogen. But since there is no d orbital and nitrogen has also this lone pair of electron left in the s orbital, so it can be donated to the other molecule or other Lewis acid. That's why nitrogen containing trivalent compounds, you have the formula NX3. So X can be hydrogen, X can be any halogen compound. They can actually behave as a Lewis base because of this lone pair of electrons. And these lone pair of electrons can be donated to a Lewis acid and it can form an adduct. So that's how from here one covalent bond can be formed and from here 3 covalent bonds can be formed. So total 1 plus 3 is equal to 4. That's why the covalency of nitrogen is restricted to 4 only. And last point is, it is unable to form any d-pi bond unlike its heavier congeners. That we have already discussed here. Since nitrogen atom does not have any d orbital, so d-pi multiple bonds is actually not formed by nitrogen. But the heavier elements, that is the phosphorus or arsenic, antimony, these are actually able to form the d-pi multiple bonds. So in next slide, we will be discussing some basic questions on the group 15 elements. So that are actually very important for the examination purpose. The first one is why is BiH3 the strongest reducing agent amongst all the hydrides of group 15 elements? Now the EH bond distances in picometer are NH3. It has a bond distance, NH is 101 picometer, PH3 is 142 picometer, arsenic 152 picometer, and antimony H3 is having a bond distance 171 picometer. And BiH bond distance hasn't been calculated yet. So as we see, increasing from nitrogen to bismuth, the bond distance between the atom, central atom, and the hydrogen is actually getting increased. And you know the bond strength, any bond strength is actually inversely proportional to the bond length. The more is the bond length, the less is the bond strength, the bond energy or bond strength you can say. So the more is the bond length, the less is the bond strength. So you see in case of bismuth H bond, the bond length is quite high, the most. That's why the bond strength of BiH bond is actually very low for a case of bismuth hydride. So in case of BiH3, since the bond is actually very much weak between the bismuth and the hydrogen, so it is actually capable to release H- ions more efficiently. So the less is the bond energy, the more efficiently the compound can release, the more efficiently the bond will be broken. So BiH3 is able to release H- more efficiently. That's why BiH3 is the strongest reducing agent amongst all the hydrides. Whereas if we go to the reverse side, NH3, so the NH bond is actually quite stable because it has the least amount of bond length. So it has the highest bond strength. That's why NH3 is the weakest reducing agent among the hydrides. So the next question is why does NH3 exhibit a higher melting point and boiling points than PH3? So NH3 is the group principal quantum number 2 and PH3 has the principal quantum number 3. Now you see nitrogen is there, and after nitrogen we have phosphorus, then we have arsenic, then we have antimony, and lastly we have bismuth. So nitrogen atom has an electronegativity in the range 3.0 in the Pauling scale, but phosphorus has an electronegativity in the range 2.1. Now nitrogen atom is also smaller in size, phosphorus atom is larger in size, because you know as we go down the group, the size of the atoms increases. Now nitrogen has higher electronegativity and it has smaller size. That's why we are having this NH3 molecule. NH3 molecule is trigonal in shape. And we have another NH3 molecule here. Now you see here nitrogen atom is an electronegative atom. That's why it is having a delta negative charge on it. and hydrogen is some electropositive because it is connected to a electronegative element. That's why there has a delta positive charge is actually getting accumulated on the head of nitrogen. Now, since we are having delta minus and delta plus between two separate NH3 molecules, there is often occurring an electrostatic interaction between this delta positive charge and this delta negative charge. This is termed as the hydrogen bonding. Since this is intermolecular, two separate molecules are actually involved. That's why it is called intermolecular hydrogen bonding. Now, because nitrogen atom is electronegative in nature, that's why the accumulation of positive charge is actually on the hydrogen, because nitrogen actually pulls the bond electron towards itself because it is electronegative in nature. That's why delta positive charge is occurring on hydrogen. And since delta positive charge is on hydrogen and delta negative is on nitrogen, so there is occurring an electrostatic interaction between the N and the H. So that is why it is called the intermolecular hydrogen bonding. So such millions and trillions of NH3 molecules can come into closer proximity and they can form this intermolecular hydrogen bonding network among themselves. That's why to break these bonds and to melt or to boil out NH3 is actually more amount of energy is required. That's why the NH3 molecule has a high boiling point. But this is not the case in case of phosphorus, because you see phosphorus is having a very less electronegativity. That's why significant amount of charge is not on the hydrogen. And phosphorus is also larger in size. So too many pH3 molecules cannot come into proximity to hold up a big chain of intermolecular network. That's why in case of pH3, such intermolecular hydrogen bonding is not possible. So the only atoms that are actually able to perform this kind of hydrogen bonding are nitrogen, which is electronegative, oxygen, fluorine, and in some cases, chlorine. Chlorine atom has a bit amount of larger size, but it has the same electronegativity as nitrogen. So that's how in some specific cases, chlorine can form hydrogen bonding. But these are the main three elements in OF, NOF. They are actually able to perform intermolecular hydrogen bonding. So that's why NH3 molecule exhibits higher melting and boiling points than pH3. So now we shall come to the next question. It is an informative question. So here, what happens when sodium azide is heated? So sodium azide is nothing but NaN3. N3 minus is the azide anion. So if we can draw the structure of N3 minus, so this is a nitrogen, and on the other half we are having this nitrogen. This nitrogen is positively charged because it is bound to four actually atoms. Four actually bonds are there. So it is having a positive charge on it. This nitrogen is negatively charged and this nitrogen is also negatively charged. So one positive charge is actually cancelled out by one negative charge and one negative charge is still there. That's why it is termed as N3 minus. It is a linear ion. And if we can draw the resonance structure here, this negative charge will fall on this. So we are having this structure also in triple bond N. So how this is the case in case of N3 minus is actually there. We are having these structures N and N triple bond N3 minus. So N3 minus is actually nothing but azide anion. So azide, when sodium azide is heated, what are the product? So firstly, you can see the thermal decomposition is the case. So NaN3, when it is heated, so molecular sodium is actually formed. So N3 minus is the one of the resonance structures that are actually formed here. And here we are having two negative charge here. And these electrons will be pulled off by this nitrogen. So here you can see here also a negative charge, a positive charge is actually counteracted by two negative charges. That's why we are having a net negative charge. That is the structure of N3 minus or the azide anion. Now, when the sodium azide is actually heated, you can see here, this is an N triple bond N. So this is actually nothing but a counteract of the case of the molecular dinitrogen. So that's why you can see this bond is actually broken quite easily and N2 is actually eliminated. That's why you can see whenever an azide is heated, thermal decomposition occurs and 3 moles of N2s are liberated with 2 moles of sodium when 2 moles of NaN3 are heated. In the next question is, how does NH3 act as a Lewis base? So in the last slide, I have told you, because of the lone pair on the sp3 orbital of nitrogen, which is actually responsible for its Lewis basicity. So NH3 molecule can act as a Lewis base. So here are the examples. The first example is actually here, when a copper 2 salt, that is actually blue in color, when it is treated with ammonia or NH3, we can form this deep blue solution CuNH3 whole for 2 plus copper tetramine complex. And the next option, next example is when AgCl, it is a white PPT solid kind of thing. When it is treated with ammonia, we can form this AgNH3 whole to Cl, which is actually soluble in water. So in these of the cases where you can see that is the NH3 molecule can act as a Lewis base, and these are the examples. In the next question, we will discuss about the different oxides of nitrogen. So since nitrogen is highly electronegative and it can form p-pi multiple bonds, so with oxygen, it forms a library of oxides. So for exams, it is actually quite important for you guys to know what are the oxides and what are the oxidation state of nitrogen in each of the oxides. So we shall start one by one. First one is the dinitrogen oxide. It is N2O, where the oxidation state is +1. Second one is NO, that is nitrogen monoxide, where the oxidation state is +2. Third one is the dinitrogen trioxide, which is N2O3. It is a bit unstable in nature, which is having an oxidation state +3. At +4, we are having 2 oxides. First one is the NO2 and second one is the N2O4. NO2 is nitrogen dioxide and N2O4 is dinitrogen tetroxide. So you see it is nothing, N2O4 is nothing but the dimer of NO2. So if we can draw this equation, we know that is the NO2, N2O4 is actually dimer of the NO2. 2 molecules of NO2 actually dimerize and form this dinitrogen tetroxide N2O4. And the last one is the dinitrogen pentoxide, which is N2O5, where the oxidation state is +5. So from +1 to +5, we are having these several kinds of oxidation states of molecule. If we draw the structure of the first one, it is N2O. And if we draw the resonance structure of this molecule, we can actually convert it to this structure. In both the cases, the structure is actually stable. The first one is actually a more stable one because it has negative charge on a more electronegative oxygen element. But in this structure, we are having electronic charges on the more electronegative, less electronegative nitrogen. So the first canonical structure is more stable. So we shall come to the next question. Apart from the noble metals, what are the metals which don't get dissolved in concentrated nitric acid? So nitric acid is one of the oxo acids of nitrogen. So you know the noble metals that are actually gold, that is Au, or platinum. These are actually not attacked by HNO3. But there are several other transition elements also that are actually not affected by concentrated nitric acid. So these are chromium and aluminium. Because chromium actually forms Cr2O3 oxide. It gets oxidized by nitric acid. And aluminium also forms Al2O3, which is also an oxide. So these oxides are actually form a layer on the outer surface on the metal. So this passive film of oxide does not allow nitric acid to actually get reacted with the metal, that is the chromium or aluminium. So in these cases, they don't get dissolved in concentrated nitric acid. In the next question, it is the proof that pH3 is basic in nature. You know, ammonia is much more basic than pH3. pH3 is phosphine and NH3 is ammonia. So in terms of basicity, pH3 is much less basic than ammonia. Still, it has some basic character. So it actually reacts with this kind of halogen hydracids, which is HX, where X is Cl or Br or I, except fluorine, the other hydrogens. So when pH3 is reacted with HX, it forms this pH4, the phosphonium salt, phosphonium chloride or phosphonium bromide or phosphonium iodide. Since it reacts with acids to form a salt, that's why pH3 is basic in nature. So these reactions are proofs why pH3 has some basic character. The next question is, what is to be done when poisonous white phosphorus comes into contact with skin? So for white phosphorus is highly poisonous in nature. So whenever it comes into contact with the skin, human skin, it actually rots the skin. That's why whenever white phosphorus comes into contact, we have actually rinse the hands with this alkaline sodium hydroxide solution, because with alkaline sodium hydroxide solution, phosphorus is reduced to pH3 and this harmless NaH2PO2, that is sodium hypophosphite salts, are formed. That's why it is less harmful. That's why whenever white phosphorus comes into skin contact, we have to rinse the hand with alkaline solution, and after that we can rinse the hands with acid solution, so the excess NaOH will be gone. Now we shall come to the group 16 elements. So this is the general trend for the group 16 elements. The first option is the electronic configuration, which is the NH2NP4. So in the last case, when it was the case of group 15 elements, it was NH2NP3. The half-filled orbitals were stable. Now we are having one more electron in the p orbital. So the configuration is NH2NP4. So in this case, you can see whenever we shall to pull off, if we can pull off the last electron from the valence shell, the corresponding configuration will be NH2NP3, which is the electronic configuration of group 15 elements. So if we have to go from 16 to 15, we have to actually pull off the last electron, or we have to provide it with the ionization enthalpy. Now, since 15 is very, very stable, so 16 will always try to go to the 15. That's why the ionization enthalpy is lower than group 15 elements. Because if we can pull off the valence electron of group 16, it will go to the highly stable electronic configuration, that is P3, from a less stable electronic configuration P4. That is, it is actually quite stable. So the ionization enthalpy of group 16 elements are lower than group 15 elements. In the other cases, it is actually quite same as group 15. The atomic or the ionic radii also increases down the group, because the principal quantum number n actually increases, and ionization enthalpy also decreases down the group because the principal quantum number increases. And another factor is actually coming here, the electronegativity factor. Here you can see the oxygen atom has a Pauling scale electronegativity 3.5. It is just less than fluorine, because fluorine has an electronegativity which is the highest electronegative element, that is having electronegativity 4.0, and oxygen atom has electronegativity 3.5. So it has a very high electronegative character. And another factor comes into picture, that is the electron gain enthalpy. Now, oxygen atom has a less electron enthalpy than sulfur because of its very small size. You see, oxygen atom is more electronegative than sulfur. Oxygen atom has a higher electronegativity than sulfur. Still, it is seen that oxygen atom has less electron affinity than sulfur. Because we are saying that oxygen atom is more electronegative, that it is having electronegative character. It actually loves electron. But we are also saying oxygen atom's electron affinity is quite less. In case of electron affinity, oxygen atom is having less than sulfur. But we are saying electronegativity of oxygen is greater than sulfur. Why is this anomaly? The anomaly generates from the fact because oxygen atom is a very small in size, where sulfur atom is quite large in size. Now oxygen atom has so many electrons in it, and it is electronegative. So if we can push one more electron into this small space, there will be electron-electron repulsion. That is not in the case of sulfur, because sulfur atom has vacant 3d orbitals. So the extra electron can be actually residing in the 3d orbital, where it will face minimum inter-electron repulsion. That's why oxygen atom, despite having such high electronegativity, is not actually fond of taking up one more electron, because it will suffer from severe inter-electronic repulsion. That's why oxygen atom has less electron affinity than sulfur, because of its small size, and because of the small size, the inter-electronic repulsion will be much high in case of oxygen. And just like the other groups also, oxygen atom shows some anomalous properties that are actually not shown by the other elements of the group. The first one is the presence of strong hydrogen bonding in water, which is not found in H2S. So we have actually discussed the similar fact here in case of in the last slide as NH3 versus PH3. So there I have told, like, N atom has a smaller size and a higher electronegativity than phosphorus. Here also oxygen atom is smaller in size than sulfur, and oxygen atom has a high electronegativity than sulfur also. So that's why this hydrogen bonding network was actually possible in case of ammonia, but it was not possible for PH3. Just like the same analogy, the hydrogen bonding network between all the water molecules is actually quite feasible, but it is not feasible at all in case of H2S. So I have actually told N, O, and F. These are the three basic elements that are actually able to form intermolecular, or you can say intramolecular, hydrogen bonding. And this phosphorus or sulfur, these are actually not able to form hydrogen bonding because they have quite large size and they have very less electronegativity. But in case of nitrogen, oxygen, and fluorine, their size is actually compact, they are smaller in size, and they have such high electronegativity, all greater than or equal to 3 in the Pauling scale. That's why in case of the NH3 or PH3 comparison, the H2O versus H2S comparison also falls under the same category. NH3 has a higher melting point and boiling point than PH3, and H2O also has a higher melting point and boiling point than H2S. And here also the covalency is restricted to 4, unlike other elements in the group. But in the most of the cases, the covalency shown by oxygen is 2. In some minimal cases, the covalency can be expanded to 4. But in most of the cases, oxygen's covalency is restricted to 2 only. So here are the different questions that are actually helpful for the exam purpose that we will discuss here. The first one is arrange the hydrides of group 16 elements in increasing order of their acidity. So the hydrides are H2O, H2S, H2AC, and H2TE. So here you can, just like the previous group 15 elements also that I have told, the bond distance actually increases from oxygen to tellurium, because the size of the atoms are actually increasing from oxygen to tellurium. So the bond distance between the central atom and hydrogen is increasing from H2O to H2Te. So since the bond between H and Te is much in length, so the bond is actually easily cleaved. That's why the acidic character of H2Te is much less than that of H2O. The other factors also come into picture whenever we are creating a kind of acid. Whenever we are talking about acid, we are forming the corresponding anion. Suppose we are having this general formula of H2E, where E can be from oxygen to tellurium. So if it has to behave as an acid, it will release this H plus and it will form this anion, that is H conjugate anion, that is He minus. So the mode will be the stability of the He minus, the mode will be the acidic character of the H2Te. Now you can see where when the E is tellurium, tellurium is very large in size and it has a library of d orbitals. And this negative charge can actually get stabilized in the d orbital quite easily. But in case of oxygen, there is no d orbital. So the negative charge cannot actually reside on the d orbital. So it has to get kept on the oxygen atom only. That's why the HTE minus conjugate anion is much more stable than the HO minus. That's why H2TE is the strongest acid and H2O is the weakest acid among the group 16 hydrides. The next question is characterizing or listing the following oxides as basic, acidic, amphoteric, or neutral ones. So we actually have classified all the oxides on basis of their properties towards water. So whenever it is actually producing a acid, when it is coming in contact with the whenever it is called a basic oxide, whenever acidic oxides are those which on reacting with water produces acids. The basic oxides are those which on reacting with water form the bases. So here, and the neutral oxides are those which are neither affected by with respect to water. It does not have any tendency to either go to acid or go to base. And the amphoteric oxides are those which are having the tendency to form both. Now you can see that's calcium oxide. Calcium oxide, if reacts with water, produces calcium hydroxide, which is a strong base. So it is a basic oxide. Na2O, when it reacts with water, it forms NaOH. So it is also a basic oxide. You can see here all the non-metallic oxides. You can see sulfur is a non-metal. Carbon is a non-metal. Nitrogen is also a non-metal. So all the non-metal oxides are actually acidic in character because N2O5 produces nitric acid, CO2 produces carbonic acid, SO2 produces sulfurous or sulfuric acid depending upon their concentration or their formology, that is SO2 or SO3. So all the non-metallic oxides will be acidic in nature. Metallic oxides in their general oxidation states are basic in nature. But if you can see the oxides of the high oxidation state, here you can see chromium has an oxidation state +6. Vanadium has an oxidation state +5. So whenever we are having oxidation state high, in case of the metal, the oxides will be acidic. But here you can see the calcium is having oxidation state +2, sodium is having oxidation state +1. So they are normally basic oxides. But whenever the metal is residing on a high oxidation state, that is +6 or +5, then the character will be acidic. Now we are having some important oxides which are neutral: carbon dioxide, carbon monoxide, or N2O or NO. These are actually also non-metallic oxides, but they are quite different and they are having some exceptional character. So you have to remember these three oxides as the neutral oxides. CO, carbon monoxide, N2O, that is nitrous oxide, and NO, that is nitric oxide. These three oxides are neutral. And here, in case of aluminium and zinc, they are form the amphoteric oxides, Al2O3 and ZNO. Both are amphoteric oxide because they react both with acid and bases. The next question is, supersonic jet aeroplanes are a possible threat towards the depletion of ozone layer. Explain. So on this Earth is actually covered with this a layer of ozone. So ozone is the one of the allotropes of oxygen, and ozone layer actually, and here if it is the sun, and from sun they are actually coming some harmful UV radiation, and this layer of ozone is actually able to actually pull off or shrug off the UV radiation that is coming from the sun. That's why the very much important for us. Without the ozone layer, without this ozone layer, the UV radiations coming from the sun will actually rip us apart, will actually produce some different kind of cancer diseases on us, and our entire universe will actually, our world will get devastated without the form of this ozone layer. So in this case, we are using the supersonic jet aeroplanes which actually produce this nitric oxide. It has been found this nitric oxide reacts with this ozone to form this nitrogen dioxide and oxygen. So it actually depletes the ozone layer. In 1980s, the scientists have discovered a hole in the ozone layer, a hole. It was a kind of alarming situation. So within 200 other countries of world actually signed on the petition that they will actually decrease the supersonic jet aeroplanes which actually use NO and the CFC, chlorofluorocarbon. So we will discuss about this more on the next session, how the CFCs can also affect the ozone layer. So the CFCs and this NO should be banned. So on 1980s, when these two things were banned, after some decade, a decade or 2 decades, it was found the hole has been again gone, and the ozone layer is actually have also come into ozone layer has been restored. That's how the world actually defeated this very much alarming situation when the supersonic jet aeroplanes were a possible threat towards the ozone layer depletion. Next question is, write down the identification test for sulfur dioxide gas. It is kind of an informative question for you guys for the exam purpose. So sulfur dioxide, when it is passed through a dark pink, or you can say violet colored permanganate solution, it will produce this sulfate. It will be oxidized to sulfate and it will be colorless Mn2. Mn2 is a pale pink color. So if a gas is actually passed through a solution of potassium permanganate, and if the permanganate solution is discolored from dark violet to pale pink, then it is the gas of SO2. So that's how SO2 is detected, or it is the SO2's identification test. So in this question, next question is, why are the wooden shelves on which concentrated sulfuric acid bottles are kept start getting stained black? So on the wooden, suppose it is a bottle of concentrated sulfuric acid, and this is the rack on which it is actually kept, and it is an wooden rack. So with further use, when we will use this and we will move the lid by a lid, so there will be some leaking of sulfuric acid, leaking of concentrated sulfuric acid that will actually come into contact with the wood. Now with further uses, this wood, the sulfuric acid will come into contact with this wood. Now you see here we are having this sulfuric acid, and when we use it, some amount or drops of sulfuric acid over the time gets dropped on the wooden board. Now this wood actually nothing but contains cellulose, and cellulose contains this C12H22O11. You know that is the concentrated sulfuric acid is one of the very strong dehydrating agent. So concentrated sulfuric acid is one of the very strong dehydrating agent. So whenever this dehydrating agent or concentrated sulfuric acid is dropped on the wooden surface, that is the C12H22O11, it actually dehydrates the wood and it actually consumes all the water molecule and carbon is actually left out. And this carbon is actually, it is black because non-metallic carbon in its elemental state is black. So that's why whenever these bottles are concentrated sulfuric acid are kept on the wooden shelf, so it will form black stain because this will be accumulation of this carbon on the wooden surface because it is a very strong dehydrating agent. The next question is, show an example where the sulfuric acid is actually acting as an oxidizing agent. Now in sulfuric acid, you see, if we can draw the structure of sulfuric acid here, this is sulfur and there are two S double bond O bonds and there are two OH bonds. So this is sulfuric acid. Now this sulfuric acid, the central atom is sulfur, which is present in its +6 oxidation states. 2 and 2 from these two oxygens and 1 and 1 from these two. Total will be 2, 2, 4. 1 plus 1 is 2. So 4 plus 2 is 6. So the central atom's oxidation state is sulfur is +6. So sulfur is residing in its highest oxidation state. Now, so the sulfur can actually come down to the any of the oxidation state like +4 or +2. Hence, it is acting as an oxidizing agent because it is itself getting reduced. It has option to get reduced. Now you can see it is this copper. Copper in the zero oxidation state is there, and sulfur is actually here as +6. So when copper metallic is actually treated with concentrated sulfuric acid, it actually oxidizes copper to +2. So it forms copper sulfate and it itself gets reduced to +4. That is the sulfur dioxide molecule. So in this case, you can see this is the reduction and this is the oxidation. From copper to copper 2, it is actually oxidation. And from H2SO4 to SO2, from +6 to +4, it is actually reduction. So that's how sulfuric acid can act as an oxidizing agent. The last question is, what happens when SO3, sulfur trioxide gas, is passed through water? And the second question is, concentrated sulfuric acid is added to calcium fluoride. So these two questions are also informative and very important for exam. First one is what? When sulfur trioxide is actually treated with water, so it forms nothing but the sulfuric acid. So that is the industrial scale preparation of sulfuric acid. When SO3 is actually dissolved in water, so this is the formation of sulfuric acid. And in the next case, when calcium fluoride is actually treated with sulfuric acid, what happens? You see, sulfate is a large anion and it has some affinity with this calcium 2+, which is quite large cation, because it lands in the beryllium, magnesium, calcium. It is an alkaline earth element which is quite large in size, and this sulfate is actually quite large. That's why calcium actually takes up the sulfate anion to form this calcium sulfate, and this H and F actually combines to produce this hydrogen halacid, that is HF. So these are the questions that I have to discuss in this chapter. And in the next session, we will be discussing about the group 17 and group 18 elements, that is the halogen elements and the noble gas elements, and that will be the end of the group, the P block elements.